Yeah, let me test actually. I think it's okay. Right, so last time I was trimming this paper. I was on part six. Sorry, part five. Last time was part five, and I think that's that's too long for a 15-page paper. But I think it's yeah. I was reading it slowly, and I think I should change my pace a bit because that's too slow. There's no way I can. I need to be able to finish a lot more paper in the future, in more in a less amount of time. So I think I need to figure out how to. I need a method to be able to read the paper back to back. Um, but in a faster way. I really want to read the details because the detail is what I'm longing for. This is the thing that I really need to understand, like the intricacies and all stuff. But probably, like the last time, my method was uh to read the paper while trying to implement the pseudocode of it. That was kind of um that took more time than I was expecting because I have to really understand the details of, I have to keep asking, hey, what was it again? What's that? And that kind of things. I think it's well, it's nice to know, like it's important, even it's important. It's quite time consuming. So I would say I would not doing it again. Maybe I'll try to explain it, and maybe just notes. Probably just like regular notes. That would should be way faster. Okay. Yeah. So last time I think I was at this in memory dot structure or something. To be honest, I have forgotten most of days, not most, like a lot of the details that I read on my previous session. But yeah, I think let's just yeah, this is the thing about reading paper. Like if you are not consistently do something about it, like you will just forget about it because even though like I count most of this, the decision, the design decision, the engineering behind it is like I'm very familiar with it's just like another system design, like quite easy to understand. and no, I mean not to not to understate the paper, but it's such a well designed paper that most people with a background in software engineering and like maybe know some design system is going to be understands. But yeah, all the details probably I already forgot. So let's like try to read like overlap from the previous section. Okay, the point seven, consistency model. If I could uh can I still open my right, open this still work? Probably I will take notes once in a while. Consistency model. GFS is a relaxed consistency model that supports our highly distributed application. Well, but remains relatively simple and efficient to implement. So it has no, so it is relaxed means eventual consistency. It's either consistency, like strong consistency like acid, or not acid. Relaxed is basically uh, non-acid consistency model. We also highlight how this guarantees related to other parts of the paper. Guaranteed by GFS. I think this part that Oh, let's zoom in. GFS file name mutation. I already, sorry, file namespace mutation. I already forgot what is file namespace is. If not forgot, I not even familiar with it. Was it the like text? Okay, I already forgot what is namespace is. It doesn't really explain anything about namespace. Like what is actually their namespacing? With is it a file? Is it like workspace, or is it like a tenant or anything? File namespace mutation. So it's like domain. If I understand correctly. I kind of not really sure. Okay, I have to keep this on. So I want to highlight namespace. Okay, creation are atomic. They are handled exclusively by master. Namespace locking guarantees atomicity and correctness. Okay, this one is atomic, meaning that, well, you cannot create the same file multiple times, right? On unspecific namespace, yeah. The master's operation log defines a global total order. Okay, this is global total order of this operation. The state of file region, which after a data mutation depends on the type of mutation, whether it succeeds or fails the mutation, and whether there are concurrent mutation. All right, so calculation is atomic, but state of file region after data mutation, so it's not atomic. Okay. Table 1 summarizes the result. Yeah, I remember this. A file region is consistent if all clients will always see the same data, regardless of which replica they are report. The region is defined after a data mutation. If it is consistent, and client will see that mutation writes in its entirety. When a mutation succeeds without interference from concurrent writers, the affected region is defined and by implication consistent. And yeah, I understand this. I read this before. I just want to actually let me just skip it because I still remember exactly what it is. Data mutation might be writes or records events, a write calls the data to be written in an application specific file offset. A record event calls the record to be appended atomically at least once in the presence of concurrent in the presence of concurrentation. So if there is a concurrentation, any appended stuff, appended data to record is atomic. But at offset of GFS choosing, in contrast, a regular append is merely a write at the end of offset that the client believes to be the current end of file. So concurrently, the offset is not always at the end of the file. It's GFS that chooses. It's GFS that chooses which region particular changes need to be written to. The offset return to the client and marks the beginning of the defined region that contains the record. In addition, GFS may insert packing or record duplicates in between, which they actually consider to be inconsistent and are typically dwarfed by the amount of user data. After a sequence of mutation, the mutated file region is granted to be defined in blah, blah, blah. Okay, applying mutation. Okay, I think I still remember this. It has mismutation. Well, wait. Using channel fair share number to detect any replica that has become stale because it has mutation while its chunk server was down in a mutation, or given to garbage collected at the earliest opportunity. Client cast through a chunk location, they may read from the stale replica before the information is refreshed. This window is limited by the cast entry timeout and the next open of the file, which purges from the cache all chunk information for that file. Moreover, as Moreover, as most of our files are pen-only, still a replica usually a parameter and of chunk rather than allocated data. When a reader returns and contact the master, it will immediately get your location. Okay. Long after successful mutation, component failures can, of course, corrupt. GFS identifies failed chunk servers by regularly handshake between master and all chunk server. It detects data corruption by checksuming. Basically, the normal heartbeat method, right? But this one, a problem by our checksuming is quite interesting. I mean, this is still on the page where the process is like behind the scene, but you know, I saw sorry, I was saying nonsense. GFS is right. Transfer preference. This is no normal heartbeat method in distributed nodes. And detector charge. Oh yeah, this was I was just, I was thinking, how do they checksuming? Like how fast you could checksum the entire replica. And data is restored from failed replicas as possible. A chance is lost irreversibly if only if all its replica are lost. GFS can react typically within minutes. Yeah, in this case, it can becomes unfillable and not corrupted. Location refer is for clear errors rather than corrupt data. Okay, 2.2 implication for application. GFS can accommodate the real-life consistency model with a simple technique already needed for other purposes, relying on append rather than overrides. Take pointing, writing self-validating, self-identifying records. Practically, all of our application mutates files by appending rather than overwriting. In one typical case, typical use, a writer generates a file from beginning to end. It automatically renames the file to permanent resident after permanent what's permanent resident? Permanent name after writing all data. So a writer generates a file from the beginning to end. It automatically renames the file to permanent name after writing all the data, or periodic checkpoint how much has been applied written. Much implied. Checkpoint may also include application level checksum. Readers verify and process only the file region up to the last checkpoint, which is known to be in defined state. Regardless of consistency, the concurrency issue, this approach has served well. According, appending is far more efficient and more resilient to application failure than random writes. Yeah, I mean, like mutating the existing record in place is dangerous. Right? Checkpointing allows the writer to restart incrementally and keep readers from processing successfully written in fixed data. File data is still complete from the application perspective. Like, so this is checkpointing. In other typical sorry. In other typical use, many writers concurrently append to a file for merge result or at least project consumer queue. Records append appended at least once. Return rules deal with this with occasional padding and difficulties as follows. Repeat part. I'll set that. Okay, let me just read it aloud. In the other typical use, many writers concurrently append to a file for merge result or as per the consumer queue. Record append at least one semantic preserve each writer's output. Because let's deal with the occasional padding and speak it as well. Okay. Okay, it's not that much. Okay, system integration. What should I take notes of? It's actually just, I'll say more details from, but more detailed information. But yeah, anyway, system instruction. We designed the system to minimize master involvement in all operation. But your file creation is master API dependent. Mutation is operation that changes the content. Let's skip this part. Okay, let's actually continue this part. Oh, sorry, I was looking at my drink. leashes and mutation order. Mutation is an operation that changes the content or metadata or a chunk as a write or a pen operation. Each mutation, okay, so yeah, it makes sense. Mutation is mutation. Performed at all chunks replica. All chunks replica means it is not propagated through the server side. We use leases to maintain a consistent mutation order across replicas. Master grants a chunk leash to one of the replicas, which we call the primary. The primary picks a serial order from all mutation to the chunk. Thus, the global mutation order is defined by the first list grant order chosen by master, and within a list by a serial number assigned with primary. Wait, so so interesting. So okay, list mutation in order. So it was like list mutation. So it was like for master gives the leases to the first chunk, in which the first chunk is going to decide wait, algorithm must follow the primary picks a serial order for mutation. So the primary is the first one that has the leases, and then it forwards, or it, how does it work? Is it like first of all, I have no idea, like the write path, is it pure client side, or like when writes happen to the chunk, will the chunk, I know, I think the chunk will also propagate to the other chunk. In what order? Like 3T chunk. So the first one is only like this one is the primary, right? And then which serial number assigned by primary? Yeah, so primary decides where should I send this first? I don't know. I think it's like less important. Like the second and the third chance, so like it's going to set whatever it gets. I don't know. The list mechanism is designed to minimize management overhead at the master. Makes sense, but what if I understand, like I don't know how, I probably underestimate how big is the Google workload, but having one master, like I don't know. Because like this one, they seems like to emphasize that, oh, we didn't want to overhead the master, we didn't want to overload the master. This is client and chunks only, man. Yeah, things like that. Server is like